All right, Algebra 2, here we go into section 2.6, and this is one that scares people a little bit at first. It's kind of a long section of notes. I'm going to break this one up into two sections. The concepts we're going to be doing here are pretty important because we're going to be doing something similar to this in almost every section that we do during the course of the year. So the title of this section doesn't tell you a whole lot. Families of functions, but this is really the important word that we're going to be talking about here, transformations. Essentially, this section is asking us, if you know what one particular graph looks like, how can you quickly come up with a transformation or just a different variation of that same graph? So we're going to talk about, I believe, 5 different ways of doing transformations of graphs, and the first one we're going to start with is called a vertical translation or a vertical shift. And what that is going to look like here, and I'll explain this here in just a minute, is this. Y is equal to f of x plus k. Now we hopefully have been getting a little bit used to function notation, which is written something like that. So f of x is going to denote something that we call a parent function. And a parent function means, or a parent graph means, one that we already know pretty well, probably one that we have memorized for each style of graph that we're going to be dealing with this year. But this particular transformation deals with what happens when a constant value that we're going to call k is added at the end of a function. And so what we can see right here is that when we are adding a k at the end of this graph, it shifts the graph of f of x up. And that's important here, by k units. Okay, so what do we mean by that? Let's take a look at something going on right here. We're going to begin, and I'm going to try to get my colors to match what I have in the notes right here. We're going to begin by graphing a function that isn't too hard for us to do, I hope. F of x is equal to 2x minus 2. So I'm hoping you guys can tell me, and by the way, sorry, let me stop real quick. If we haven't talked too much about this, the f of x function notation is really just taking the place of a y. So you can really think of this as y equals 2x minus 2. So I'm hoping you guys remember this and recognize this as a linear function, and it's in slope-intercept form. Our y-intercept is that negative 2 right there, so I would go down 2 units and make my first point there. And the slope of that linear function is positive 2. Thinking of it as a fraction, that'd be 2 over 1. So from our y-intercept, we would go up 2, right 1, and put our next point right there. And I always like to do that a few more times. Up 2, right 1, up 2, right 1, or from the y-intercept, we could have gone down 2, left 1, down 2, left 1, and that would have worked. So this is what the original function in this problem is looking like. So that's the graph of f of x is equal to 2x minus 2. Now, the interesting thing that we're talking about in section 2.6, though, is what does it do to this graph if you add a 4 after the f of x? So back to the previous slide we just looked at here, you can take a function and add a constant value, which we call k at the end, and that will shift your original graph up by whatever k is equal to. And in this case, we're adding 4 at the end of this function. So in red now, I'm going to graph what the function f of x plus 4 would look like. Every single point that we graphed in blue, I'm now going to shift 4 units up. So we started with our y-intercept that was right here at negative 2. I'm just going to move that point up 4 units. 1, 2, 3, 4. This is the y-intercept of my new function. And every point that we had, like this one here, I'm going to slide that up 4 units. And this point here, I'm going to slide that up 4 units. And this one here will go up 1, 2, 3, 4 again. This guy will move up 4 units. There we go. And now I have a new set of collinear points. So I'll go ahead and draw this graph right here. And what we have there in red is the graph of y equals f of x plus 4. That graph has been moved. Let me switch to a different color right here. That graph has been moved 4 units up from every point on the existing graph right here. Up 4. And you wouldn't want to label this because it gets messy, but that point moved up 4, that one moved up 4, that one did, and that one did. The entire graph went up 4 units. So the big idea to take away from here, let me leave that there, is that by putting a plus 4 at the end of the function, we shifted our original blue graph up 4 units. And that's what a plus 4 at the end of a function does. Let's see that in a slightly different way. Now, this is where I sometimes confuse people a little bit. If you're not sure what this function here, g of x, is supposed to look like, g of x is equal to x minus 4 quantity squared minus 2, don't panic. These are the kinds of functions. I'm kind of using this section here as kind of a springboard. These are the kinds of functions that we're going to learn to graph in almost every different chapter that we're going to do during the year. So I'm not expecting you guys to know right now how to graph this. I'm going to go ahead and give you the graph of the original function, and what you're going to be working on now is coming up with the transformation. So what we're going to learn probably in October, I would say, is that this is what we call a quadratic function. And a quadratic function takes a shape called a parabola. So what I'm doing here in blue, you guys don't really have to worry about right now. This will be given to you. But this is a parabola with a vertex that is at the point 4, -2. And it's an upward opening parabola that looks something like this. Now again, you don't have to know how to come up with this. That's going to be given to you. But that in blue is going to be the graph of g of x. This function right over here. So now that that's been given to you, our job is to graph y is equal to g of x and then minus 3. So what we just got done talking about on the last problem is that if there was a plus 4 at the end, that's going to move you up 4 units. This time we're subtracting 3, and that means that we are going to shift this graph down 3 units. So that k value that's added or subtracted at the end of the function is always going to be a vertical shift. Now watch how easy this is, guys. I'm going to take a look at that blue curve. If you remember, I started with this vertex right over here. I'm just going to drop it down by 3 units. 1, 2, 3, and this now is the vertex of g of x minus 3. That was really the only point that I used to come up with that blue graph. So I'm just going to draw the exact same shape in blue, except I'm now going to do it in red, starting at this new vertex. So basically, guys, I'm going to grab this curve and move it down here like this. Now that's something I can do on this software that you guys can't, so we're going to go ahead and just draw that in there. And it's going to look something like that on the right, and something like that on the left. Basically, every point on that blue curve has been brought down 3 units. Okay, so a minus 3 at the end of your function is going to bring you down 3 units. And looks like I had one more for you here too. Okay, just thought I'd use this chance to show you guys a little bit of trigonometry here. H of x, our new function, is cosine of x. And this is something we're going to be doing pretty late in the year, guys, maybe March or April if I'm not mistaken. So again, for right now, you don't have to worry about how I'm coming up with this, but the graph of cosine starts right about here. And let me see if I can get my spacing right. 1, 2, 3, 4, 5, 6, and a little over 6 units to the right. It hits another spot at the same one right there. And then let's see, right about here. The graph of cosine is a wave, everybody, that's going to look something like this. And I won't be quite as careful, but it does something really similar over here on the left. So that is the graph of h of x equals cosine of x. So don't worry about that. That'll be given to you here in this section. Our job is to come up with the graph of h of x minus 2. So ask yourself, what's happening at the end of this function after the h of x? They're subtracting 2. And that means that we're going to drop this entire graph down 2 units. So every point that I had in blue, I'm going to just drop it down 2 from where it was. So that point right there, this point right here, this one, and like I said, I didn't get real specific with it, but this graph is going to take the same shape as the blue graph, but everything's just being dropped 2 units down. So it's going to look something like this and this and this, and I'm just trying to come up with a graph now that's the same shape, the same size, but just moved down 2 units. So that's vertical transformations, everybody. When there's a number added at the end of a function, you move it vertically that far. If it's a plus 2, you would move it up 2, but since it's minus in this case, we move it down. Okay, so that is what vertical transformations look like. The next one we're going to talk about here, horizontal translations. And this one shows up a little bit different right here. This one looks like this. And you'll notice the difference between what we just did a moment ago and what we're doing now. Now there's a number added or subtracted, but it is inside the parentheses. It is directly acting on the x. So if you see a function y is equal to f of x minus h. That's how we read that. That minus h in the parenthesis tells us that we're shifting the graph of f of x to the right by k units. Sorry guys, my spacing is a little weird right here when I switch from smartboard over to the iPad. So an x minus h in parentheses is a horizontal shift. I'm sorry, that is a typo right there. That should have been h units to the right. And then just a variation on that right here on the bottom. If it's f of x plus h, the plus means we're actually going to shift left by h units. So with horizontals, it happens inside the parentheses, and it's always the opposite of what you might think. A minus h means we're actually going to the right, and a plus h means that we're going to the left. All right, so let's see what that one looks like in action here. Okay, so again, this is a function we dealt with earlier today. This is one you guys should know how to graph. F of x is equal to 2x minus 2. So again, my y-intercept is negative 2. My slope is up 2, right 1. So I'm going to try to make a few points right here. Okay, that's pretty good. And then we'll go ahead and draw the original function. That wasn't very good. We're going to try to draw the original function now passing through. Slightly better, not much. There you go. Now, here's our job today. We're supposed to graph now y is equal to f of x plus 3. So there's a 3 that's being added, but since it's inside the parentheses, not a plus 3 at the end, that would be something different. Since there's a 3 added inside the parentheses, I'm looking at this case right over here. That is a horizontal shift, and it's shifting every point in the graph left by h units. And our h here is 3. So that plus 3 tells us that we are moving our original blue graph left by 3 units. So again, every single point, like for example my y-intercept at negative 2, I'm now moving to the left 3 units, and that's how I'm going to begin this graph. So every point I'm just sliding 3 to the left, okay, and it's going to look something like this, and now I should have another series of collinear points, so I go ahead and connect those dots, and this in red right here is the graph of y equals f of, and that's going to be x plus 3. It's identical to the blue graph, but it's being shifted 3 units to the left because that plus 3 is inside the parentheses. Let's do another one. Here's another graph you guys haven't seen before. Maybe you saw this in Algebra 1, but I kind of doubt it. This is called an exponential function, and it's something that we're going to be graphing later on in the year here, guys. So for an exponential function, again, this part will be given to you right now. The one and only point that's really important is right there at 0, 1, and we get a graph that kind of looks something like this. That's a graph that we say is increasing at an increasing rate, and it's got what's called a horizontal asymptote. That's a funny word. Right over here at the x-axis. That's a line that the function approaches but never actually touches. Okay, that'll be given to you, so no need to panic about that. Our job, come up with the graph here of y is equal to g of x minus 4. So 2 things to notice. There's a minus 4 here, and then also notice where that minus 4 is inside the parentheses. And that's a horizontal shift, and horizontal shifts are different from what you might think. A minus 4 means that we are actually moving to the right 4 units. So take a look at this blue curve here. We're going to shift the whole thing right 4 units. There's not much to do here. I started with this initial y-intercept here at 0, 1. I'm now going to move that point 4 units over to the right and go from there. Other than that, you guys, everything else stays the same. So the original blue curve just gets shifted 4 to the right and is now going to look something like that. It actually has the same horizontal asymptote there at the x-axis. Okay, everything is just pushed 4 units to the right. So really all we're doing in this section, guys, is we're moving an existing curve in one direction or the other. We just have to figure out whether it's up or down or left or right. Okay, so that's 2 of the 5, I think, transformations we're going to make. We did vertical shifts, and then we just did horizontal shifts. A third one we're going to talk about here, a vertical reflection. And this is what happens when we have y is equal to the opposite of f of x. So the important thing here is if you just have a negative out in front of your entire function, that reflects the graph of your original function over the x-axis. So a graph, however it looked before, is now going to flip over the x-axis and look something like this. So if it was up here in the first quadrant, it now flips and ends up down here in the fourth quadrant. If it was in the second quadrant, it flips down now into the third, and so on and so forth. So let's see what that one looks like. Okay, a linear function here again. So this is one I could ask you guys to come up with on your own. Y equals negative 2/3 x plus 4. Okay, so our y-intercept is positive 4 right there, and our slope is negative 2/3. So I would go down 2, right 3, and put a dot, down 2, right 3, down 2, right 3, and that's probably pretty good for right now. So I'll go ahead and draw the line passing through those 4 collinear points, and there is our original function, everybody. Okay? All right, so that's the graph of f of x. Not really important for us today. Our job is to come up with the graph of y equals the opposite of f of x. Meaning, let's go back to what we just wrote. When you put a negative in front, we take this entire graph and we reflect it over the x-axis. And the x-axis, of course, is the horizontal axis. So this graph is going to spin around that point there. Now, little trick to that. The first thing I want to do is focus on this point right here, which is our x-intercept, and I think I've got that at the point 6, 0. If you were to try to flip this line vertically now over the x-axis, that point isn't going to move at all. It had a y-coordinate of 0, and when you take the opposite of 0, you still get 0. So that point doesn't move at all. But now if I focus on this point, I want you guys to notice that that point is 2 units above the x-axis. Flipping it is now going to move it 2 units below the x-axis. So that point reflects over the x-axis to right here. This point, which was our y-intercept at positive 4, flips over the x-axis and is now going to be a y-intercept of negative 4. And then this point that we came up with over here, it was the fourth point I think we came up with, that had a y-coordinate originally of negative 2. It's 2 units below the x-axis. So when we flip it, that point is actually going to move up and end up 2 units above the x-axis. So now if you take a look at these 4 red points that we've plotted, they are collinear as well. So we'll go ahead and connect them, and that, everybody in red, would be the graph of y equals the opposite of f of x. Whatever your y values of the original function were, in red now they are the opposite. Positive ones like this now turned negative. Negative ones like this guy now turned positive. But 0 stayed 0. So that's how you do a reflection over the x-axis. I'll put that back there. Okay, so that's what that graph looks like. And one more example of this same concept right here. Okay, this is another trigonometric graph that we're going to get to later in the year. G of x is equal to sine of x. It looked a lot like that cosine of x graph that we did a few problems ago, but this one starts right here at the origin. So if that's the graph of sine of x, our job is to come up now with the graph of the opposite of g of x. So what did we talk about a second ago? Every point that was on the x-axis stays on the x-axis. Even when we're flipping this thing around the axis that way, a point with a y-coordinate of 0 stays 0. So these points that I'm highlighting right here in red, this is everywhere that the original graph of g of x touched the x-axis, and its reflection then is still going to touch the x-axis. But this point right over here, guys, the first peak of the sine wave at 1, that now flips down and is now below the x-axis at negative 1. This first low point right here had a y-coordinate of negative 1. That now flips up here to positive 1. And you can kind of see where I'm going. This little trough, it's called, the low point right here, now flips up here. And here was a peak that is now going to flip down here. So my reflection of this graph, everybody, over the x-axis is just going to take that pretty blue curve and flip it upside down to make this red curve instead. So that red graph is y equals the opposite of g of x, or y equals the opposite of sine of x. All right, so hopefully we get some sense for what that thing looks like up until this point. Okay, that's probably a good place to wrap up this video, guys. When we come back and do the rest of this, we've got horizontal reflections to talk about, and then we have vertical stretching and compressing. But that's a wrap on this first part of the video. We'll pick the rest of this up with our next one.